So, whenever we talk about making AI smarter, giving it more knowledge, right? Making it more factual.
Stopping it from just making stuff up.
Exactly, stopping the hallucinations. We're usually talking about, well, the heaviest lifting you can imagine. We're talking about training.
Which is, I mean, it's the bottleneck for the entire industry right now.
It really is. You're picturing these massive clusters of H100s just humming away in a server farm for months.
Millions of dollars in electricity.
Millions. Just to update the weights of a model so it knows something that changed yesterday, it's this massive, clunky, expensive process.
And the worst part is, the second you finish that training run, the model starts to rot.
It's instantly out of date.
It becomes a time capsule. The moment that training finishes, that model is frozen. It doesn't know about the news story that broke 5 minutes later.
But what if you could make a model significantly smarter, I mean dramatically smarter, without changing a single wire in its electronic brain?
Without touching the weights at all.
What if you could take a frozen model right off the shelf and make it perform like a model that's 10 times its size just by handing it a book?
And that is the entire premise of the paper we are breaking down today.
I'm so excited for this one.
It's titled In Context Retrieval-Augmented Language Models, or you'll hear us say In Context RALM. This is coming out of the team at AI21 Labs researchers Ori Ram, Yoav Levine, and their colleagues.
And the mission for this deep dive is, I think, really specific and important. We're not just going to look at the results, which are, frankly, mind-blowing.
They are very impressive.
We are going to dissect the methodology. We want to get under the hood and understand the architecture. How do they actually build a system that lets a standard off-the-shelf model access the internet or private data without any retraining whatsoever?
Right. We're looking at the engineering decisions. I mean, mechanically, how do you insert a search engine into the middle of a neural network's thought process? It sounds kind of wild when you say it like that.
It does. But before we get into the how, let's really establish the why. Why do we need this RALM thing in the first place? I mean, a lot of our listeners have probably heard of RAG, Retrieval-Augmented Generation.
Sure. Everyone knows RAG.
You put a PDF into a chatbot, and it answers questions about it. How is this different? What's the problem this paper is solving?
That's a great question. And to get it, you really have to look at the fundamental flaws of a standard language model, an LM, when it's just operating on its own.
You mean like a GPT-2 or OPT or Llama?
Exactly. When they're closed book, so to speak.
Yeah.
They suffer from 3 major blind spots. First, and this is a big one, is a lack of attribution.
They can't cite their sources.
They can't. A standard model is just this black box of probability. You ask it a question, and it predicts the next sequence of words based on this giant soup of training data.
Right.
It can't point to a specific sentence in a specific book and say, I learned it right here. It just knows it, which makes verification, impossible.
And that leads directly to the big one, the one everyone talks about.
Factual inaccuracy.
Hallucinations.
Right, especially on more obscure topics. If the model hasn't seen a specific fact thousands of times during training, it might just make something up that sounds plausible.
Because it's designed to be fluent, not truthful?
It prioritizes fluency over truth, exactly. And then there's the third one, which we already touched on, which is that frozen state.
Frozen knowledge.
Yep. If you download LeMay 2 today, it has no idea who won the last Super Bowl. And historically, the solutions to this problem were, well, they were really heavy.
Use systems like Retro, right?
Retrieval-Enhanced Transformer, DeepMind did some fantastic work there. But the thing with Retro is it requires you to change the actual architecture of the AI.
It's not a plugin.
Not at all. They introduced this whole new mechanism called chunked cross-attention.
Which means surgery. You're performing brain surgery on the model.
That's a perfect analogy. Major surgery. You can't just take a pre-trained model like Llama and turn on Retro. You have to build a Retro model from scratch, train it from scratch, and maintain that whole separate pipeline. It's a huge barrier to entry.
Okay, so that's one option. What was the other one? You mentioned KNNLM.
Nearest neighbor language models. Yeah, that's kind of the brute force approach.
How does that work?
You effectively store a vector representation for every single token or word in your entire training corpus.
Wait, every single one?
Every single one.
That's a storage nightmare. That can't be practical.
It's intractable for most production use cases. I mean, you're talking about petabytes of high-speed memory if you want to index the entire web. It just doesn't scale.
Okay, so the landscape before this paper was basically either perform brain surgery on your model with something like Retro, or build a hard drive the size of the moon for KN and LM.
And that is precisely why this in-context RALM paper is so exciting. It proposes a third way. It says, let's leave the model weights completely alone.
Don't touch the brain.
Don't touch the brain. Let's just change the environment the brain is operating in.
Okay, let's unpack that. Let's get into the high-level approach.
Yeah.
How does this actually work if we're not touching the model's weights, its theta?
So the core innovation here is really simplicity. The authors call it a zero-effort document reading mechanism.
Zero effort sounds good to me.
It sounds great, right? And the recipe is basically 3 off-the-shelf components. That's it. First, you take a frozen LM.
Any LM.
Any of them. GPT-2, GPT-J, OPT, LMA. Doesn't matter. You treat it as a strict black box.
Okay, so component 1, the brain.
Second, you take a document retriever, a search engine. This could be a Wikipedia search API, a Google search API, or, a private Elasticsearch cluster with your company's documents.
Component 2, the library.
And third, and this is the magic, you combine them at the input stage, not inside the model, before the model.
Okay, so visualize the data flow for me. In a normal chatbot, I type the capital of France is.
Yeah.
The model sees that and it predicts the next word. What happens here?
So in this architecture, the system basically intercepts your input.
It jumps in the middle.
It jumps in. Before the model even sees the capital of France's, the system takes that little bit of text, treats it as a search query, and runs to the library.
So it does a retrieval step first.
Instantly. It finds a relevant document.
Yeah.
Let's say it's a Wikipedia snippet about Paris. It takes the text from that snippet, and it effectively pastes it before your sentence.
Wait, so the prompt the model actually sees isn't just my sentence.
No.
It's something like, here's a Wikipedia article about Paris, the capital of France is.
Exactly that. And then it asks the model to predict the next word.
Oh, that's clever. So the model is effectively reading the document in real time to inform its answer.
Yes. And because language models are trained to do one thing, predict the next word based on the context that came before it. If the context you give it literally contains the answer,
It's going to use it. It's the path of least resistance.
it grounds the entire generation in the retrieved text.
It sounds almost deceptively simple. But I know with all things in engineering, the devil is in the details. You can't just paste random text in and hope for the best.
No, you absolutely cannot. And that's where the methodology gets really interesting. There are these very strict, very specific architectural decisions that make this whole thing work.
Right. Let's go there. Section 2. The key steps in the methodology, because I have a ton of questions about the actual mechanics. My first one is, does it look up a new document for every single word it generates? Because that sounds exhausting.
That is the first critical design choice they had to make. And in the paper, they call it the retrieval stride. They denote it with the letter S.
Stride, okay, like in convolutional neural networks, right? How big of a step do we take between lookups?
It's a very similar concept. They had to figure out the right frequency of retrieval. I mean, imagine you're the model. Do you want to stop and run a Google search for every single syllable you speak?
No, that sounds incredibly slow and inefficient.
It's computationally prohibitive. If you retrieve for every single token, you're calling your search engine thousands of times just to write one paragraph. The latency would be unbearable.
Okay, but on the other hand, if you only look something up once at the very beginning of a long conversation,
Then you run right back into that static context problem. If we start off talking about the capital of France, but then the conversation shifts, and we start talking about the economics of the Eurozone,
that original document about the Eiffel Tower is now useless.
it's completely irrelevant. So they needed to find a sweet spot, a balance between the freshness of the data and the computational cost of getting it.
So what do they find?
They tested this extensively. They looked at strides of 1, 2, 4, 8, all the way up to 32, and they found that a stride of 4 was the optimal balance point.
A stride of 4. So every 4 tokens, that's roughly every 4 words.
Roughly.
That is still incredibly frequent.
It is aggressive. It really is. It means every time the model generates, a short phrase, the system pauses, looks at what's just been written, grabs a new document, updates the context, and then continues.
Wow. That creates a very high-resolution grounding for the model. It's like it's constantly checking its facts.
Resolution is the perfect word for it. This high-frequency retrieval grounds the model in super high resolution. It keeps the model on the rails, so to speak.
Right?
If you wait too long, if you use a stride of, say, 16 or 32, you're giving the model too much time to just drift away into a hallucination before the next fact check comes in.
Okay, so that's step 1, the stride. We check the library every 4 tokens. Now for step 2, Formulating the query, what do we actually type into the search bar?
This is the retrieval query length, and this is another one of those areas where your first intuition might actually lead you astray.
That's so.
Well, you might think, just take the entire conversation history and use that as the search query.
That seems logical. More context is better, right?
Yeah.
Context is king.
Context is king, but noise is the enemy. Think about it. If we've been talking for 20 minutes and I take that entire transcript and just shove it into a search engine, the very specific thing you just asked about.
Like, who is the current CEO of NVIDIA?
Right. That specific question is going to get completely washed out by the thousands of words that came before it.
It gets diluted.
Totally diluted. The search engine will return documents that match the general vibe of our whole conversation, not the specific fact needed to predict the very next word.
So we have to limit the query. But if you limit too much...
That's the other side of the coin. If you just search for the last word, NVIDIA, you have no context. You might get a document about some character from Roman mythology, not the graphics card company.
So once again, we are looking for a Goldilocks number. Not too long, not too short.
And again, they tested it. The authors found that using the last 32 tokens was the optimal length for their best retriever.
32 tokens. So that's roughly, what, 2 or 3 short sentences?
About that, yeah. It's enough to capture the immediate subject and predicate, like the stock price of NVIDIA just closed at, without getting distracted by what we were discussing 5 minutes ago about France.
It really focuses the search on the now.
Precisely. The assumption is that for the task of predicting the very next word, the most relevant information is almost always contained in the immediate past.
Okay, so we have our stride, which is 4. We have our query length, which is 32. Now we get to step 3, the search itself, the retriever. And this is the part of the paper that really threw me for a loop.
You and me both. This is one of those findings that I think makes you really rethink the current hype cycle in AI.
I mean, we are constantly being told that vector search is the future. Embeddings, semantic search, dense retrieval.
Right.
There are entire companies, multi-billion-dollar companies being built right now just to provide vector databases.
And for good reason in many cases. Dense retrievers, models like BERT, Contriever, Spider, they are amazing at understanding meaning. They can find documents that are conceptually similar even if they don't share a single keyword.
But this paper, they tested those high-tech, fancy neural retrievers against what?
Against BM25.
Which is, remind me.
It stands for Best Match 25. It's an algorithm that dates back to the 1990s.
The 90s.
And it is, for all intents and purposes, just a very fancy form of keyword matching. It looks for exact string matches. If you type apple pie, it looks for documents with the words apple and pie. It has no idea what an apple is. It just matches the symbols.
Okay. And in this paper, for this specific task of in-context RALM.
BM25 won.
Get out.
I'm serious. The 1990s keyword search beat the state-of-the-art neural nets.
How? That seems completely counterintuitive. I mean, AI is supposed to be smarter than just matching keywords. Why did it win?
It really comes down to the very specific nature of what we're trying to do here, which is language modeling. Remember, our goal isn't just to find a document that's generally about this topic.
Right.
Our goal is to predict the next word with perfect accuracy.
Okay.
And very often, when you're trying to predict the next word, you need a precise fact, a proper noun, a date, a name. If I say the winner of the 1998 World Cup was, having a document that vaguely talks about the emotions of football in the late 90s is totally useless.
You need the document that literally contains the string France in 1998 World Cup.
You need that exact string. And that's where BM25 shines. Keyword matching acts as a much stronger filter for these specific entities.
So the dense retrievers can sometimes drift off into topical similarity instead of sticking to factual exactness.
That's a great way to put it. BM25 is ruthless. If the word isn't there, it doesn't retrieve the document. And for next token prediction, that ruthlessness is actually a feature, not a bug.
And there has to be an engineering benefit here, too.
A huge one. BM25 is computationally almost free compared to running a neural retriever.
Really?
Oh, yeah. Neural retrieval requires running a heavy transformer model just to process your query and search the index. BM25 is basically just a lookup table. It's incredibly fast and cheap.
So it's better and faster. For this specific job, that's the holy grail.
In this specific architecture, yes. It was a surprise, but a very welcome one.
All right, that brings us to step 4, the integration. So we've used our 90s keyword search to find a document. Now we have to actually feed it to the model. You said we paste it in front, but models have a context window limit. You can't just keep pasting stuff forever.
Right, you'll run out of room. This is the concatenation step, and it involves a pretty important trade-off. To make room for the new document at the front of the prompt, you have to delete something else.
What gets the X?
The oldest part of the user's input, the very beginning of the conversation.
So it's a sliding window, the new document comes in the front, and the oldest part of the chat history falls off the back.
Exactly. The system is constantly maintaining this context of retrieved document, plus the most recent user context. It prioritizes what did we just find and what did you just say.
So it's sacrificing long-term conversational memory for immediate factual accuracy.
Which, for many, many tasks, is exactly the right trade-off to make.
You know, this whole architecture relies on some pretty big assumptions, though. We're kind of treating the model like it just magically understands what we're doing.
It does, and we should talk about those.
Let's move to section 3. Important assumptions and design choices. What's the biggest one?
The biggest one by far is assumption 1, generalization without training.
Yeah. We're assuming that if we just paste a random Wikipedia article in front of a sentence, the AI will know, oh, I'm supposed to use this as a source of truth. But it was never explicitly trained to do that.
Correct. This relies on a concept called the inductive bias of in-context learning.
Okay, inductive bias. That's a term we hear a lot in machine learning. Can you break it down for us in this specific context?
Sure. Think about the data these models were trained on. The common crawl. Basically, the entire internet.
So web pages, news articles, blog posts, textbooks.
Exactly. And what is the fundamental structure of, say, a news article? You usually have a headline, maybe a summary paragraph, and then the details follow. Or think of a textbook. You get a definition in bold, and then the next paragraph explains it.
So the model has seen this pattern billions and billions of times. Information at the start of a block of text explains the information at the end.
Precisely. The model has naturally learned that text appearing earlier in a sequence is often context for the text that follows. We are exploiting a behavior that it already has.
So we don't need to tell the model, hey, use this document for your answer.
We don't. We just put it there. And the model's own attention mechanism naturally gravitates toward it because using that information is the easiest way to lower its perplexity.
Perplexity being its level of confusion or uncertainty.
Right. The model just wants to be confident in its next prediction. If the answer is sitting right there in the prompt, 2 inches from where it needs to write, the model will essentially cheat and copy it.
So we're basically weaponizing the model's innate desire to be lazy.
We are giving it an open book test and banking on the fact that it would much rather read the answer than have to guess it from memory.
Okay, that makes a lot of sense. Now, what about assumption 2? You mentioned the query length earlier, using the last 32 tokens. That seems to assume that recency is all that matters.
That is the recency bias assumption. The entire methodology is built on the idea that the information at the very end of the prefix is the most relevant signal for the search.
Which is probably true, most of the time.
Most of the time, yeah. But not always. If I try to refer back to something we said an hour ago, hey, remember that specific guy we talked about at the beginning? This system is going to fail.
Because that guy isn't in the last 32 tokens.
Exactly. The context is gone. So in context, RALM is fantastic for maintaining factual continuity in the present moment, but it might struggle with long-range callbacks within a single conversation.
But it's a calculated risk.
It is, and the authors found that for the core task of language modeling, just keeping the text flowing and factual relying on that recent context prevents the signal dilution we talked about. It's the right trade-off.
I just want to circle back briefly to the comparison with those other methods. We mentioned retro and KNN-LM. I want to make sure the listener really gets the magnitude of the difference here.
The difference is really about parameter efficiency versus architectural complexity.
So KNN-LM requires storing a vector for every single token in the training data.
Right. That's a storage bottleneck. It's a database that scales linearly with your training data. If you train on 1 trillion tokens, you need 1 trillion vectors in your database. It's just huge.
And retro requires actually training new special parameters inside the model.
Retro is a fantastic idea, but it locks you in. If you spend $10 million training a special retro model, and then a week later OpenAI releases GPT-5, your model is already obsolete.
But with in-context RALM,
you just delete your old model, you download GPT-5, and you plug it into your existing retrieval script. It's model agnostic.
Wow.
And that is the killer feature. It future-proofs your entire retrieval system. You're not tied to any one model architecture.
Okay, let's get back to the methodology itself. We've established that BM25, the simple keyword search, was the surprising winner. But let's be honest, keyword search isn't perfect. It has some pretty famous blind spots.
Oh, it definitely does. It has what's called the lexical gap problem. If you search for the word canine, but all the relevant documents say the word dog, BM25 will miss them completely.
So did the authors just accept that limitation?
No, of course not. This is what leads to Section 4, refining the methodology. They realize that simply taking the top one result from BM25 is a bit risky. You might get a document that has all the right keywords, but is about a completely wrong context. The classic search engine fail.
We've all been there.
Right. So to fix this, they introduced a reranking phase.
A reranker. Okay, so how does that work?
So instead of just taking the single top document from the search, they ask the retriever for the top K documents. Let's say the top 16 results.
Okay, so we cast a wider net. We get 16 candidates to choose from.
Exactly. And then they use a really clever method to figure out which one of those 16 is actually the best one for the job. They propose two ways to do this. Method A is called zero-shot re-ranking.
And zero-shot implies we're still not training anything new.
That's right. For this method, they use the language model itself to judge the quality of the documents.
Wait, the student grades their own study guide.
In a way, yes. Here's the process. You take your top 16 documents, you pair each one of them with the user's recent context, and then you ask the language model a question.
What's the question?
You ask it, how predictable is the next sentence, given that I've just read this document? You're basically asking it to calculate a probability score.
And how does the model know if a document is good or bad?
Well, LMs are probability machines, right? They assign a score to how likely a sequence of text is. If I give the model a document about internal combustion engines, but the user is talking about jaguar animals, the model will try to predict the next few words and find that the connection is really unlikely. The text doesn't flow.
So the probability score will be really low.
Exactly. But if the document is about big cats of the jungle, the model sees the user's input and says, this makes perfect sense, this flows perfectly, and it assigns a high probability score.
So we just pick the document that makes the model the most confident about what comes next.
Yes. We pick the document that minimizes the model's perplexity. And the most fascinating part of this is that they found you can use a tiny model to do this sorting for a huge model.
You can't.
Yes. You can use a small, cheap GPT-2 model to act as the scout. It quickly goes through the 16 documents, picks the best one, and then you pass that winner over to your massive llama model for the final generation.
That saves a ton of compute. You don't want to run the big, expensive model 16 times just to check documents.
Precisely. But if you do have the resources and want even better performance, there's Method B, predictive reranking.
And this one involves a little bit of training.
A tiny bit, yes. This is what they call the specialist approach. They took a small BERT-like model, a Roberta model, and they trained it on one specific task.
What was the task?
To predict one thing. Will this specific document help the main LM predict the next word correctly?
So they literally built a dedicated talent scout.
Yes. And as you might expect, this specialist predictive reranker outperformed the zero-shot method. Because it was trained for that one specific job, it learned to spot helpful information even better than the general LM could on its own.
So the fully optimized pipeline is search with cheap BM25, re-rank with a small, smart specialist model, and then feed the one perfect document to the big genius model.
That is the state-of-the-art pipeline, exactly.
Okay, let's talk numbers. This is what everyone wants to hear. Section 5, the results. All this clever engineering, the stride, the query length, the re-ranking, the surprising win for BM25. Does it actually make the AI that much better?
This is where it gets really, really interesting. They measure the improvement using a metric called parameter efficiency.
Which is just a fancy way of saying how big does the model act. Yeah.
Exactly. How much bang for your buck are you getting? And they found that using this in-context RALM method with off-the-shelf BM25 allows a model to match the performance of a vanilla model that is 2 to 3 times its size.
Wait, say that again, double or triple the size?
Yes. For a specific example, they took a 345 million parameter model, a pretty small one by today's standards. When they gave it this retrieval method, it outperformed a 762 million parameter model that didn't have retrieval.
That's already very impressive. But usually, with these kinds of techniques, the benefits diminish as the models get bigger.
That's what you'd expect, but that's not what they found. The effects scaled up. They tested an OPT model with 6.7 billion parameters.
Okay, a respectable mid-size model.
When they gave that 6.7 billion parameter model this retrieval capability, it matched the performance of the 66 billion parameter OPT model.
Hold on. You're saying a 6.7 billion parameter model performed like a 66 billion parameter model.
That's what the perplexity scores showed.
That is a 10 times improvement in effective power.
In terms of its ability to predict the next word on a complex dataset, yes. A 10x multiplier.
That completely changes the economics of AI. It's staggering.
It really is. It suggests that a huge portion of those 66 billion parameters are just being used to memorize trivia and facts. And if you can offload that memorization task to an external search engine,
Then the actual reasoning part of the brain doesn't need to be nearly as massive.
you don't need a Godzilla-sized brain if you have a library card.
I love that. And they didn't just test this on next word prediction, did they? They looked at actual downstream tasks.
They did. They tested it on open domain question answering, standard benchmarks like Trivia QA, and natural questions.
And what did they find there?
They took LAME 13b when it was closed book, meaning it was just relying on its own internal memory. It got about 12% accuracy on one of the benchmarks.
12% is basically failing.
It's not great. But then they turned on in context. RALM gave it access to Wikipedia snippets related to the questions. Its accuracy jumped to 31%.
From 12 to 31%, that is the difference between a useless toy and a genuinely useful product.
And you have to remember, this was completely zero shot. The model was never trained to answer questions. It just figured it out on the fly because the answer was sitting right there in the text they gave it.
That is wild. But as we always say on this deep dive, there is no free lunch. There's always a catch. Let's head to our outro and talk about the trade-offs.
There is always a trade-off. And in this case, the essential trade-off is between training cost and inference cost.
Okay, break that down for us.
So on the training side, you win big. You pay $0. There's no fine-tuning, no renting out giant GPU clusters for months. You save millions.
But you pay for it later, at runtime.
You pay the tax at inference. Every single time a user asks for a response, you are now running a search engine. And crucially, you're feeding the model a much, much longer prompt because you're pasting in entire documents.
And longer prompts mean higher compute costs and slower speeds from the model itself.
Exactly. If your prompt is normally 50 tokens, but you paste in a 200-token document, the model is now doing 5 times the work for every token it generates.
Plus, you have the latency from the retrieval stride. If we're searching every 4 tokens, the whole process has to pause constantly to go fetch new data.
It definitely slows down the raw speed of generation. It adds latency. So the core trade-off becomes, do you want a model that is very fast but kind of dumb and forgetful, or a model that's a bit slower but is infinitely smarter and always up to date?
But wait, there's a counter-argument to that, isn't there? Based on what you said earlier about the smaller model acting like a big one.
And that is the saving grace. This is the key. Because you can use a much smaller model, say a 6 billion parameter one, to get the same quality of results as a huge 66 billion parameter model. The math often works out in your favor.
Right. A 6 billion parameter model is way faster and cheaper to run than a 66 billion one. So even with the added tax of the search calls, you might actually be faster and cheaper overall.
Exactly. The total cost of small model plus search can be much lower than the cost of giant model. You are shifting the computational burden from parameterized memorization inside the model to active retrieval outside the model. And it turns out retrieval is usually cheaper than massive matrix multiplication.
So what's the final thought for our listeners? What does this methodology really mean for the future of AI development?
I think it means that the era of the static, monolithic AI model might be coming to an end. We don't need to wait for GPT-5 or GPT-6 to get access to facts about the world that have changed. We don't have to be held hostage by training cutoff dates anymore.
We can make the models we have right now, today, smarter.
We can turn these dumber, smaller, open-source models into absolute geniuses just by giving them the right pair of reading glasses. And the provocative thought for anyone listening who's building AI applications is this: maybe stop trying to fine-tune your own model on your company's data. That's expensive and it's brittle.
Instead, just build a better search engine for your prompt.
Exactly. Focus on the retrieval. Focus on the context you provide. The model already knows how to read. You just need to give it the right book at the right time.
I love that. It really democratizes intelligence. You don't need a supercomputer to train a new model from scratch. You just need a library card and some clever Python code.
And a good implementation of BM25, apparently.
There you have it. The paper is In Context Retrieval-Augmented Language Models by the team at AI 21 Labs. A true masterclass in doing more with less.
Absolutely. A phenomenal piece of work.
Thanks for tuning into this deep dive. As always, keep diving deep.
See you next time.